Okay. Okay, in our last class, I explained about the definition of magnetic dipole moment by the running current from the rectangular shape. So if we have a rectangular loop, current loop, inside of the magnetic field, can find some torque acting on these loops. And by this definition, and by comparing the torque resulting in a dipole moment, we can define the magnetic moment by the dipole moment with the current loop is defined by current multiplied by the area. And I explained this current loop generate magnetic moment, and which one is physically equivalent to the magnetic moment of the real permanent magnet. And these two, the generated by the current loop and from the permanent magnet is not, they are not distinguishable. So that means it's physically equivalent. And also, if we have a motion of the electron, not the positive charge, the direction of the angular momentum is, let's say, the positive z direction. In that case, the magnetic moment by the this electron motion is the opposite direction to the angular momentum. But somehow they are parallel, and only the difference is the direction. And the ratio between the angular momentum and the magnetic momentum is defined by the gyromagnetic ratio called the gamma, and is consisted by the very basic quantity, the charge of the electron and the mass of the electron. But if we consider the total angular momentum, not only the angular momentum, total angular momentum means including not only the angular momentum, but the spin momentum. So in that case, we can replace L to the total momentum J, and this simple value is changed to the with the Landau G factor. Okay, so in a previous class, I just explained about the motion of this angular momentum inside of the magnetic field, and many students feel difficult to understand more details. So I made some more detailed calculations here. Okay, so let's think about this current motion. If we have some loop and the current is rotating, or the current is flowing this loop, or you may assume there is some charged particle with the circular motion. And let's say this tilted axis is called the G. Here, the direction of the magnetization is confined in a XG plane. This is the definition of our coordinate system. If we take a look the motion of the charged particle, let's say there's some charge Q, they're rotating something like this in an XY plane. We always can define the motion of the XY plane if we have a circular motion. Then the position R of the charged particle is defined by this simple relation. And if you define the velocity v of this charged particle, you can easily write down the direction of v, this direction. R is this direction. So those two vectors are orthogonal. You can easily confirm it by taking the inner product between them. So you can generate 0. So they are always orthogonal. And now let's think about that. The force acting on this circular motion charge. Now the B field is xg plane, so they are not the g direction. They have some x component. So it's not that simple compared to the circular motion of the charged particle with the g direction magnetic field. Okay, so you can easily calculate this equation by multiplying. Here is the V, and the B is here. This is a simple vector algebra. You can keep the magnitude, and if you're taking the cross product between them, we have there is two terms and two terms. So we have 4 terms, but the vector product between this x component and this x component will be disappeared because they are parallel. So we have 3 remaining part. Let's say this x direction, and taking the y direction, we have a minus y. So this came from, we have 2 minuses, so we have a y-axis. And if we multiply this term and those terms, they are disappeared. And taking the cross product, this component with this one, we have a cosine phi sine theta, y multiplied g generate the x-axis. And the final one is cosine phi sine theta, and y multiplied x generate minus g. So we have a minus n here. So it's a tedious calculation, and we are interested about the torque, not the force. So we have to calculate this one again. So again, or you may calculate by this is the triple cross product. So you can see we can obtain something. And okay, let's write down. If you are familiar with this cross product, it's more easier, but let's do it directly. So we have a R here with cross product of this one. So we have a 6 component, but this is the basis vector is only 3. So let's do it term by term. So multiplied by this cosine phi to here. So this is a multiplication of x and y. So they generate g. And so on. There are many, many terms. But here, this torque is torque acting on this single point in this point, right? And the total torque acting on this loop, we must taking the integral of the torque acting on this small point. So this integral taken from 0 to 2 pi for this azimuthal angle. Then let me ask a simple question. What's the result of this integral? Yes, the question of the definition of theta. Definition of theta is here. Is it okay? And please answer to me. What's the result of this integral? Yes, it is 0. Yeah, it is 0. You can easily imagine by the symmetry, let's say sine phi generates this one. And actually this is the, yeah. So this integral means something like this. So it should be 0. Very important result. And as you see here, I'm sorry, the writing is not so good, but we have a multiplication of cosine phi with the sine phi here, and cosine phi here, cosine phi here. And but this is the expression, and those are expressions, so multiplication will be disappeared. And now we have a cosine phi and cosine phi. So we have a sine square phi, sine theta with the x multiplied by y term. And let's just consider this part. They generate, this is y, so it's going to 0. And this one and this one generate another cosine, sine, multiplication of cosine and sine. So after integral, they are going to 0. And this one and this one is also 0 when we take in the integral. So only the remaining part is this one. So this integral give us and just a moment. This generate. This is the g-axis. So we have a, sorry, this is g direction, and you have a minus sign here. So this is generate. This is minus y, so we have a y direction and integral of cosine square phi d phi with the sine theta. And this is generate 1.5. Is okay? The integral of the sine square phi from the 2 pi generate 1.5. This also very famous relation. Okay, so finally what we can obtain is Q, V, B, R have sine, theta, and y direction. Okay, and we have another relation. The V, relative V, what we have to is we taking the time for one circular motion, it should be 2 pi r. So the relation, the v is 2 pi r divided by the time t. Oh, we have a missing q here. So this result, if we replace v to 2 pi r over t, can rewrite r square b and half sine theta. Okay, so we drop this 2, vector 2, and pi r square is nothing else the area of the circle, and q over t is actually the current. So they generate I multiplied by area. So this is nothing else but the mu, the mass moment by the definition. Okay, so this is a summary of this calculation. But I don't want to give this result to students because you have to do it by yourself. So when I upload the my lecture note, I will skip this page. I will give only this page. So please do it by yourself. Probably it is a good question for the maybe midterm exam. Okay, so now we have this result. The total torque is represented by mu multiplied the cross product by the vector b. It is very general form. It doesn't matter the real direction of b and the motion of the any kind of motion. So if you assume the motion of a particle is not circular, let's say the rectangle or any arbitrary shape, you can easily define the loop of the current by dividing small circular motions. So any circular motion those part, sorry, let me, yeah, if we have two circular motion by the nearest one, and contribution by this part and this part to the total integral will be cancelled out because the direction is opposite. So that means if we have any arbitrary shape of the closed loop, you can fit out by this circular motion, and only the remaining part is the outer motion, outer contour, outer path. So this expression, the definition of mu is I, a vector. They are very general one. You can apply this relation to any kind of the current loop, any shape of the current loop. So if you have some current loops, you can define the mass moment generated by this running current. So now let's forget about this circular motion. Now let's focus on only the result of the magnetic moment. And then we have such torque, and as a result, you have now we are talking about this one. Underneath of this angular momentum, we have a circular motion here. But just ignore this part. Very confusing. So the direction of torque is, let's say this is a B, and torque is and the direction of this torque is perpendicular to the mu and b. They are mutually perpendicular to mu and b, or they are perpendicular to the plane made by those two vectors. So we have a b vector here and b vector here. We have some plane here. And those torques are perpendicular to this plane. And let's take a look this circular motion again. Now we have a B in a Z direction. And the angular momentum pointing to here. And this is the plane made by B cross the mu cross B. And this is the torque. They are all orthogonal. This is a upper view of this means these circles. And here, if the angle is phi again, and the length of tau is multiplication of this length with this L. So now the length of dl or d tau is this length multiplied by the sine theta generate this length. This is nothing else but this one. So this is actually mu sine theta. Okay. And this length, if the phi is the small enough, we can multiply phi here. So this is the length of this arrow. And the angular velocity of this motion, we can define the omega L. Nothing else but d phi dt is omega L. So this d phi can be replaced by omega L dt. Now we have a dl L sine theta omega L dt. And what is the dl dt? dl dt is the torque of the system. If if we take the time integral to the angular momentum, we have a force. If we take the time integral, time derivative to the angular momentum, we have a torque here. So that's the definition of torque. So that means the torque is L sine theta omega L. And we know the relation between the L and mu here. Here, L is gamma over mu. So let's write here. And the left-hand side is torque tau. This is the mu cross B. And now we have gamma mu sine theta omega L. Okay. So here, this is the mu B sine theta again. So if you compare those two, left-hand side and right-hand side, you can obtain omega L is here. Okay. So you can obtain the relation of this precession angular velocity with the magnetic field. Okay. So, let me back the definition of the gamma again. Here, the gamma is defined by charge, the ratio between the magnetic moment divided by the angular momentum. So the unit of this gamma is charge divided by the mass, like this. So let's back to here. So I just said the unit of gamma is charge divided by the kilogram, right? And the omega L is the angular frequency. The unit must be hertz. And the unit of B is the Tesla. So let's confirm it. Gamma is C over divided by the kilogram. And B, unit B is Tesla is, let's say, recall this relation. And the unit of Tesla is Newton divided by charge Q and meter per sec. So if we multiply those two terms and drop the Coulomb, and the Newton is nothing else but kilogram meter per sec square. So let's read that again. And we can drop this one. So we have a 1 over s. That's the unit of the hertz. Okay. So please keep in mind, if we multiply the gamma to the magnetic field, you can always obtain the unit of the frequency. That is very important. If you multiplied h bar here, that's the unit of the energy. So if we multiply the h bar to here, you can obtain the energy scale. So in many physics, frequency means nothing else but the energy of the system of the many physics. So higher frequency means higher energy. So let's keep in mind that part. Okay, so any questions so far? I'm sorry about those many mathematics and many equations, but that's necessary to understand more details. Yeah, it is okay. Then let's move on. Okay, so far we are talking about the angular motion. We have a charged particle in a solid state. They always have angular motion, and now we learn those angular motion generate magnetic moment. But that kind of angular moment, the magnetic moment is not dominant in many ferromagnetic materials. But just keep in mind that part. And also, I should mention about the spins. You know, the real magnetic moment is defined by the sum of the angular momentum and the spin momentum. Now I'm talking about the spin momentum. Let's imagine the electron. And classically, spin means the rotation of the if we have a electron with the finite size, and if they are rotating, then it's you can model by the charged the circular motion of the charged particle. If you assume the electron is uniformly charged by the amount of this charge, and if they have a circular motion, you can obtain the magnetic moment generated by those charged particle model. That's quite classical. And actually, it's not easy to find the radius of the electron by the classical model. But somehow, you can calculate this integral. This is the not simple integral, but that's not so that's not impossible. Somehow, if you calculate the magnetic moment generated by those circular motion, then the value is, you can obtain some value. Here, mu b is the Bohr magnetron, which is defined here. But we obtained 5/6 of the mu b. Yeah, actually the magnetic moment of the spin is determined by the experimentally, and we already know the moment is mu b. So there is something missing part. Okay, so we cannot explain the spin, the property of the spin by the classical model. Classical model means the rotating sphere, rotating charged sphere. And quantum mechanically, I'm gonna give a very brief review of the quantum mechanics in maybe next class. But by the Schrödinger equation, there is no way introduce the spin. But spin is necessary to explain the experimental observation. So people decide to introduce this spin, the fourth quantum number, introduced by the hand. It's not very natural. They just assume, oh, we need such quantum number. So when you solving the Schrödinger equation, spin doesn't appear naturally. But experimentally, we call the Stern-Gerlach experiment. I'm gonna explain it later. The experimentally this compound, we need such physical quantity. In relativistic quantum mechanics, when people introduce relativistic quantum mechanics, we have to solve the Dirac equation. And when you solve the Dirac equation, you can obtain, we need such a spin quantum number, and quantitatively, the magnitude of the magnetic moment of the spin is exactly same to this Bohr magnetron. And this Bohr magnetron is another definition is, if we think about the first Bohr orbit defined in a hydrogen atom, we have such angular momentum, then we obtained this Bohr magnetron. So the Bohr magnetron is the unit of the magnetic moment of the spin or electron. And if we have a circular motion of the first Bohr orbit, then we can obtain the mu b value, the Bohr magnetron value, by from the previous definition, means the multiplication of the current and the area. So this is the if we call your memory, this is the current I in this form, or in previous calculation. If you insert the radius r and the velocity v by definition of Bohr magnetron, you can obtain this term. Oh, see, there's no v here. Yeah, something like this. Okay. So, I just very briefly explained about the spins, then I will give more details later. let's focus on paramagnetism. I said we have to understand the ferromagnetism, but in order to understand the ferromagnetism, we have to start from the paramagnetism. Okay, so I want to recall this cartoon again. We assume each atom has angular, they have some electrons, many electrons, and they have some circular motion. So that means they have some magnetic moment. Actually, this magnetic moment came from not the circular motion, but mainly came from the electron spins. But somehow, let's assume the magnetic moment in the atom. And if we think about the identical atoms, we can assume the magnetic moment, the magnitude of the magnetic moment are identical. And how about the direction? The direction of the magnetic moment, if we have a symmetric system, then there is no reason they pointing out to the special direction. So they are pointing direction to any direction. So that means the average of this magnetic moment should be 0. So there is no preferred orientation. That should be 0. But if we applied magnetic field, that means we break down the symmetry of the system. There is some kind of certain direction. This direction is different to other direction. So now we call this anisotropy. We have some preferred direction, and when we have a spin in this direction and in other direction, they have a different energy. So in nature, the total energy must be minimized. That's the very basic rule. So if we consider the magnetic potential energy, they form its shape. I didn't explain about this magnetic potential energy, but it's very general form. So the potential energy of U is defined by the inner product, not the cross product, inner product between the magnetic moment and the magnetic field. So those simplification implies the magnetic moment, this magnetic moment has a small energy when they parallel to the magnetic field. So that means this spin, this magnetic moment has a lower energy than this one. So they are starting to align to the direction of the magnetic field. Okay, then you can think about it. If we apply the small field, then all magnetic moment prefers the align to the spin direction, the field direction. But as we already explained, the nature also preferred randomness. That's called entropy. So we have to think about that part. So in a certain non-zero temperature, we have some rules, thermodynamic rules called the Boltzmann distribution. Continuous variables. So the Boltzmann distribution say there is some kind of a distribution in a given temperature T. We call this KBT is the thermal energy. This thermal energy always prefers the random direction. And this energy E means they have some potential energy. And if you this is the probability function of this Boltzmann equation. So as you see here, if we have a low energy, there is some large probability, but still we have a finite probability for the high energy portion. So if we assume there's no interaction between the moment, this direction of the magnetic moment of the atom should follow this Boltzmann distribution. and they want to try to align the magnetism to the field direction also. So if we have a zero field, the moment are random, so all they have all equal distribution. So if you're taking the integral or taking the average, it should be zero. But if we have a certain amount of V field, the energy difference from the parallel and anti-parallel are different, and the difference between those parallel and anti-parallel has increased by the magnetic field. So those gap is nothing else mu b multiplied by 2, because they are those gap are mu b plus mu b, those are minus mu b. So the total gap is 2 mu b. So those lower energy, there's more population, and in higher energy, there is less population. So when, if you want to taking the average of the some physical quantity in a certain probability distribution, what we have to is taking the average, the integral with this physical quantity with the probability function. And this is the normalization factor. Okay. So we already know the P. And the energy, we want to calculate the direction of the magnetic moment to the given field direction. So we want to calculate the projection of the mu to the direction of the field. And also here the energy E is the potential energy of this term. Okay. And the integrand is d omega, means it's the angle, the solid angle integral, but we have a symmetry to the, we have a b direction here, and we have a symmetry to the horizontal angle. So those are actually sine theta, d theta, phi, and d phi. It can take in just 2 pi. And those 2 pi are dropped in top and bottom, so we can ignore this angle. And we have a cosine inside of the exponential, and cosine here, and cosine here. So it looks like very, very difficult integrals, but fortunately we have a sine theta d theta. So that means if we define cosine theta to new variable t, then we have those relations. So you can do calculation by something like this. Let's say this. Okay. So they are not that difficult integral. So let's skip details, but you can do it. Okay. So as a result, this integral gives us this result. We introduce new variable s with this those part. those parts. Actually, I already write down the equation in this form. This one turned to be this form here. S is here. So, what's the physical meaning of this S? That's important. The KBT always means the thermal energy. If you have a higher temperature, they have a higher energy. And the thermal energy making the system to be a random. And this mu B means the potential energy because of the external field B. So they prefer the direction. So large S means we have a strong magnetic field and the system preferred aligned system. And large S we can obtain when temperature is going to 0 or large field. They have a same effect. In small S means the temperature is high and magnetic field is small. Okay, and this cotangent S minus 1 over S, we define the new function called Langevin function. That's another French name. So maybe the Langevin is quite correct pronunciation. Sorry about that. And anyway, the average magnetic moment of the parametric material is defined by the this form here. Mu m is the magnetic moment of each atom, and this line function is defined by this form. Okay, so here we have a relation, mathematical expression of the cotangent S for the small s. If the S is small, then we have such approximation. And the Langevin function is minus over S. So these terms are cancelled out, and this is the leading term of the Langevin function. So this is linear. So that means this curve. Okay. And the slope is 1 over 3. So that's why we have a 3 here, then we got a 1. But this is only valid for the small s. Small s means we have a large temperature or small field. Okay. So in that case, the magnetic moment of the system is nothing else but the average magnetic moment multiplied by the number of atoms here. And okay. And in a Langevin function is replaced by this simple number s by the s over 3. So the m is in this expression. And also the magnetic moment can be expressed by the susceptibility and magnetic field. And here we write down the magnetic moment in this form again. Here, then we have this one. So that means the magnetic moment, the magnetic susceptibility is this form. Here, the m is magnetic moment of each atom and number of moment and permeability of the vacuum. And this KBT means the susceptibility of the paramagnetic material. They have a inverse proportionality to the temperature. Small s, only valid for the small s, means high temperature. So, anyways, the susceptibility, if we measure for the paramagnetic material, you can obtain 1/T dependence. That's the important result. If you have a low temperature susceptibility getting higher and higher. So that means if you apply the magnetic field, you can obtain the larger magnetic moment. Okay. So this paramagnetic susceptibility is generally very small. It's a 10 to minus 5 something. And so it's usually negligible in many cases, but in a real experiment, if we making some films in a substrate, in that case, the contribution is not ignorable because of this large volume compared to the magnetic materials. But okay, so that part is not so important for the student. This is important for the researchers. So let's forget about this comment. And if you have a small temperature and high B field, means large S. So this expression is not valid anymore. We have to talk about this part. But still, this expression is quite still similar to these lines, and those term is a leading term. So still it is valid in many cases. Okay? So that's what we call 1/T susceptibility. Let's move on to the plastic materials. So far, we are talking about this paramagnetism behavior, these motions. Here, this cartoon, we have a random direction, random orientation of magnetic moment without without external field. But when you apply the external field, we have a average, the magnetic moment pointing some special direction, and this average value for the special direction is proportional to the external field. And this proportional constant is what we call susceptibility of the response function of the system. Okay, so let's think about the ferromagnetic material. The ferromagnetic material means the direction of the magnetic moment of the atoms are all parallel for long distance. In a ferromagnetic material case, they are all random, but even though they look random, but somehow the average value pointing some direction. That's the definition of the paramagnetic material. But in a ferromagnetic material, they are all parallel together. Then, how they can be achieved? As I already mentioned, such aligned or ordered state, the entropy is decreased. So physically, it is not favorable state. So in order to overcome such inconvenient, we need extra energy. We need something more. That's the origin of the physical origin of the ferromagnetism. Okay, so now we are working on classical physics. So I'm going to explain this origin by frame of the mean field theory. Mean field theory means if we have many atoms, then let's pick one single atom. And all contribution from other atoms, we can take the average. That's the meaning of the mean. So the field generated from all other atoms can be simply expressed by those forms. They are proportional to the mass moment itself, and as a result, they generate some kind of extra field. That's called the molecular field, or atomic field, or eventually they go into they are called by the exchange field. Anyway, so now we have some assumption. There is some strong interaction between those spins. This is assumption. And in a mean field theory frame, they didn't mention why the interaction is exist, but they just assume, okay, there is some internal field between them. That's the assumption. And I'm gonna explain why in a later. So we can model this interaction internal field by the extramolecular field, and they have a form of the this simple relation. And as a result, the total field of the system is external applied field and extramolecular field. I'm sorry about the confusing the H field and the V field, but sometimes I'm using the H and sometimes I'm using V, but eventually they are same meaning. So we recall the previous result. The mass moment of your sample is proportional to the H or V, and the proportional constant called the susceptibility, and they are inversely proportional to the T. Now we have a similar relation, but this H field replaced by this total field, applied field, and the extramolecular field. And this molecular field is lambda m again. So we have a m in the right hand side, in the left hand side. So let me do simple math. So here m is substitute. So if you move to this term to the left hand side, okay. Okay, here, Okay. So now we have a M in a right hand side again. So in order to obtain the susceptibility, we need some trick. So anyway, somehow the result of the susceptibility has this form. The different thing is here the susceptibility is inverse to the temperature, to this form. But here we have a TC, so that implies certain temperature called the TC or called the Q temperature, the susceptibility going to infinite. That's the divergence. So if we have such divergence in a field, means there's some phase change. So the role of this external magnetic field, the extra molecular field, is shift to the origin of the inverse proportionality of the T by the amount of the Tc, which one is called Q temperature, and this Tc is proportional to the lambda. Here, lambda means the proportional constant of the molecular field, and the C is the Curie constant in paramagnetic materials. So experimentally, you can obtain the TC by measuring the vanishing of the ferromagnetic material, ferromagnetism, and the puzzling point is the magnitude of the lambda. If you know the magnitude of the lambda, you can easily imagine the size of the molecular field. And if you think about the dipole interaction of the dipole field because of this magnetic moment, you can imagine, you can calculate the magnitude of the lambda. But the experimentally obtained Q temperature, you can obtain the lambda value is about 1,000 times larger than the classical physics. That's the problem of the mean field theory. But somehow, this inverse proportionality, the temperature, is well explained the experimental observation. So I'm gonna explain this part in next view graph. But now here and time for the questions. Today I gave a lot of mathematical expressions. Maybe students have some problem to understand. So I'm gonna give a homework for those derivation for the student. Okay, anyway, so it's time for the questions. Please ask questions. Okay. So the question is, why they have a minus sign here? That means, as I explained, if you have a paramagnetic here, this is 0. So if we have a minus sign here, this axis is shifted like this, and this is Tc. So this equation is susceptibility for the ferromagnetic material for the high temperature over the Curie temperature. They are valid only in this part, in a higher temperature. This expression cannot apply to this part. Below the Curie temperature, actually the susceptibility in this definition is already divergent. So this equation here, the minus sign means finite Curie temperature. So there is some possibility of the existence of the ferromagnetic phase in finite temperature, below the Curie temperature. Okay. For the 10th question, actually they are same quantity. Here, this lambda means the proportional constant for the extramolecular field. They are proportional to the magnetic moment of the atomic moment. And here lambda is came from here. If we have a lambda m here. Okay. Oh yeah, we already here. So those lambda actually we write here this relation, and those. So this lambda actually this term, so we can rewrite lambda c here. So if we divide the c in both sides, like this, and this is nothing else but the inverse of the susceptibility of the for the paramagnetism. I'm sorry, now I'm a little bit confusing, but somehow you can find this relation in this form. And this lambda is came from this equation. Now I didn't do it, but you can do it. It's a simple math, but now I'm a little bit confusing. If you're taking some simple mathematical trick, you can easily obtain this result. So that's the kind of the dilemma in a classical mean field theory. We cannot explain such large value of lambda by meaning of this model. The same one. In a previous page, I give a dose energy. That is called the potential energy, or in other words, they are called the Zeeman energy. They are exactly the same one. One or two more questions, please. Paramagnetic material, they have some preferred direction of the magnetic field. If the magnetic field itself is uniform across the sample, their magnetic direction is always parallel to the magnetic field. But if they have some non-uniform I'm sorry, I have some network problem. Yeah. So anyway, I think the time to end of the lecture. Okay. Anyway, I will upload some homework for the student, which one is related to the content of today's lecture, and more details you can find in a LMS system. Okay. Yeah. Okay. So I will, after I upload the homework in a LMS system, I will notice on a KakaoTalk. Okay. Then see you next Monday. Okay. Bye.